The next thing that we want to take a look at is this idea, this phenomenon called the photoelectric effect. And this is something that had scientists a little bit confused because they had observed that if you shined light on certain materials, mostly metals, that you could actually cause the metal to lose some of its electrons. You could basically ionize it with light. But the problem was this light had what was called a threshold frequency. And so as you can see here in the picture, you've got the surface of a metal here in the figure. This gray surface down here at the bottom is the surface of the metal. And if you shine higher energy light, like purple or green, then electrons sort of pop off the surface. And the higher the energy that the light was, the more speed these electrons would have as they kicked off. But all of a sudden, if you made the light too low of an energy, no matter how bright you made the light or how long you shined it, no electrons would ever be ejected. So there was this kind of minimum frequency or this minimum energy that was required, and you had to be above it. If you weren't above it, then you did not see the effect at all. It was like a brick wall. There was no effect at all until a certain point, and then all of a sudden you would see the effect, and then again, the higher energy the light was, then the faster the electron would get thrown off. So again, this kind of confused people here. And so in order to explain this, Albert Einstein came along, and he proposed that light is not purely a wave, that it actually has this second component to it that makes it sort of particle-like. And so he said we can't think of light completely as waves, we have to think about it as particles as well. And he called his particles of light photons. And so basically, photon is to light as atom is to matter. So the atom is the smallest piece of matter that has unique properties, or we could go further and go down to the electron and the proton, whatever you want to do. But these are the smallest pieces of the thing that you're studying. So in this case, for light, the smallest piece of light is a photon. And again, what we're saying here is that the energy of light is actually not related to the amplitude. So earlier I said that if we were studying water waves or sound waves, we would also want to think about the amplitude, so how high up and down the wave was oscillating. But with light, the energy is really proportional directly to the frequency. And so he came up with a very similar equation to what Planck had come up with, except he took his n out, and he said if n is 1, this gives you the energy of a single photon. And so basically what Planck was saying before was when you multiply it by this n, is that you're just getting a certain number of photons. So if you multiply in Planck's equation, if you do 4 times h nu, then that would just be the energy of 4 photons. And h, again, is Planck's constant, so he basically reused that. And the other thing that is important here is that we can take our C equals lambda nu formula, and we can solve it for nu and get C over lambda, and we can replace nu with C over lambda. And so, again, combining our two formulas here gives us energy in terms of wavelength. And now we can see that energy and wavelength are inversely proportional. When I divide by a bigger number for wavelength down here on the bottom, I'm going to get a smaller number for energy, and vice versa. So this explanation of light that Planck and Einstein kind of built is called a quantum theory because it implies that light cannot be transmitted continuously, that it has to be transmitted in these discrete packets, these discrete particles, these discrete chunks. And so you can't have a fraction of a photon. You can't have half, just like you can't have half of an oxygen atom, you can't have half of a photon of light. Now, the problem with this is that we couldn't just abandon the wave model either, because light definitely exhibits other things. Light does things that only waves do. And so things like diffraction and interference patterns, we're not going to get into all that in this course, that's more physics, but there are lots of things about light that can only be explained if you think about light as a wave. And so what we need to do is we have to be mentally flexible here, and we have to think about this wave-particle duality, this idea that we have to think about light simultaneously as both. It's a wave and it's a particle, but we have to think about them simultaneously. And so again, we can calculate the energy of a photon, but we need its frequency to do it. And so there's part of the wave component there, there's part of the particle component.